Hello, everybody. Hi, everybody, for getting here. Welcome, everybody, and welcome all everybody who's here and also in the room, but those who are connected online. Thanks for connecting for this talk. And I'm delighted to introduce you to. Are you hearing okay?
Yeah.
It all set up. Okay, everybody can hear, I imagine, yes, in the connected people, yeah. So I'm delighted to introduce Hector Orengo. Hector is one of the few and top computational archaeologists in the world. There are not that many.
Not that many, yes.
And it is, well, great privilege that we have him here at BSc with the Computational Social Science and Humanities lab. Hector is a full professor in ICREA that joined just since January BSc. Prior to that, he got his PhD at la Universidad Rovira i Virgili, then went into different places in Europe, but most notably the University of Cambridge for some time, also leading projects in computational archaeology. And came back then to the ICAC, one of the CERCA institutes, an institute of Institut Català d'Arqueologia Clàssica, and now finally is here at BSc, and we're very happy to have him, and I very much look forward to this talk.
Okay,
thank you, Hector.
Thank you very much. I hope this is not taken as my presentation to the BSc because I'm going to try to talk a bit about. Okay, first thing you are going to notice is this is going very slow because the presentation is hosted on the cloud. Okay, but it's going to be slow, but hopefully it will go more or less. It will not hang. So I will try to offer an interpretation of the states of the humanities in relation to computational analysis. As you know, I'm now intending to lead and create a group on computational humanities inside the social sciences and humanities department, directed by myself. And okay, during these last months, I've been thinking. Most of my work has been on history, mostly archaeology, some archival stuff. But for me, it's also a new field in general. I studied also my degrees in history. I did some philosophy, some anthropology, some art history, but and lots of archaeology. But now I have to relearn lots of stuff to be able to see what's going on in the wider humanities field. Okay, so I'm going to try to discuss some current geospatial approaches and trends applied to archaeology, because this is the basis, the core of my work. But I think many of these insights might be applicable to other fields of the humanities. And I'm going to try to show current trends using case studies, my own work. And I will try to reach some basic general conclusions. Let's see how it goes. Try to move this part. It's not possible. Okay, so go back. So lately, during the last years, computational humanities are getting quite in fashion. This is probably due to the increased availability of data. We have lots of new data, but also collection methods and sensors. Everybody has a mobile today with a camera. Some mobiles even have LiDAR, laser recording systems, new types of scanners, drones. There's also new methods of data analysis, machine learning, agent-based modeling. At the same time, the availability of computational power has been increased, but also the way to access this computational power. There's lots of cloud computing services. There's, as you know, the number of HPC centers in Europe is increasing during the last years, and it will increase during the next few. So there's also a big movement towards open data. With an emphasis on fair data. And that's thanks in being part of Merced, pushing the movement. And there's also an interesting point, the generational change. Let's say younger people are more prepared to deal with all these changes and to take advantage of them, while older professors like me are a bit at the queue of this revolution. Okay, let's see if this moves. Yeah. However, in the humanities, computational analysis have been focused on very few fronts, mostly natural language processing and text analysis. Large language models, this is more debatable. They did not originate, they are mostly into the computation area, but they require a high input from the humanities in corpus design, in curation, annotation, prompt engineering, evaluation. Okay, so we have a big contribution and the need to use humanities approaches for the development and an improvement of evaluation of LLMs. Without any doubt, geospatial and temporal analysis have been highly benefited from these new trends. Quantitative historical approaches, although they have not always been very well conceptualized, because they have tried to use massive data without much curation. So many cases, the results have not been spectacular. There's lots of approaches from image, audio, multimedia work, and also curation, preservation of humanities data, and presentation of humanities data. But this is more general with all the disciplines. So what makes humanities data special? I'm sorry to those that were in my seminar on humanities data, because this is the same slide and some of the points are the same. But well, the first thing is that there's no big data in most humanities fields. Okay, we have textual corpora, but beyond that, there's very few disciplines that can produce big data sets, and this is because humanities data are very diverse. We have, for example, pottery collections. Until the industrialization, there's no pot that are the same. Okay, so they are all very different, and it's very difficult to standardize it. Also, the same with lithic material, which is what people was using, the tools that people were using before the Neolithic. So most of the biggest part of humanity's history, paintings, there's no equal. No, they cannot even be made equal. Okay, so they are very diverse between types, but also within types. That is, you can have 2,000 types of pottery types. Okay, but within each type, they are all different. Okay. This is a very unstructured data. Okay, it's in many cases we have very little information of the use of this data. We only know how this data was recovered, how where this data was. In terms of other kinds of humanity data like paintings, we have lots of information of who painted it, when, but we don't know why it painted it or for which reason. Or in many cases, we might know lots about the paintings, but as you move through you go to the past, you know less and less and less. So 99 of historical humanities data, it has basically no information. You can have very large corpora like textual data to very, very few art collections, ethnographic, material culture. So basically the large corpora are usually focused on textual data. Okay, but for example, when you do an archaeological survey, which is many archaeologists walking on the fields, collecting every piece of pottery they find in the ground, they can collect millions of pottery pieces. So this is a very large corpora, but every piece of pottery is different. You cannot draw 1 million of pottery pieces. You have very few information on this. And if you had to to get a pottery expert with every little piece of pottery and try to get as much information as possible, like with chemical analysis, that would be eternal. So we are talking about a very complex type of data. The last thing is that there's no digital born data, okay? These are physical elements, they are real. I mean, in many disciplines, we work with data that, I mean, in the social sciences, economy, in politics even, many types of data are digital born. In the humanities, there's very few digital born data, okay? So when you deal with real objects, interpretation is all. What do they mean? You know, what does a pottery piece mean, or a lithic, or a painting? They don't have a meaning themselves. They give us information about what it means to being human. Okay, this is in a way very interesting, because the only questions we can deal with are very general questions about human behavior and nature over time. Okay, digitalization is an issue. For example, when you digitize using a laser scanner, a piece of metal or a piece of stone, you are leaving huge amounts of information. You are only acquiring the form. Okay, when you are digitizing a text, you can include lots of information, not just the meaning of the text, but also the type of letter, the support. But usually digitalization leaves lots of information out. So it's very difficult to capture the nature of cultural data, okay? And those working with art, they know. So at the bottom, the way in which you define your data features, the objects you are studying, it's a kind of matrix of different approaches and scanning methods, okay? So these objects cannot be interpreted directly. They have to be used as proxies of a question you want to use to answer using this data. Okay, I will make some examples of this. So for example, let's say you have an archaeological site. In many areas of the world, these archaeological sites have they have a shape like a small hill, a mound. Okay, if you are using LiDAR, a scanning method, what you are going to collect is the shape of the object, but not its nature, because there are lots of shapes like roundabouts that have exactly the same shape, but are not archaeological objects. So you have to define different ways to record the object. For example, multispectral image analysis, proximity to roads, radar texture, to be able to have a definition based on the source of this object. Okay, so all these sources are just a proxy of the object. At the same time, the object, it's a proxy of something else. You are not interested in the mound itself. You are interested in what the mound is telling you on a cultural level. For example, how people live, where do they live, what is the size of the settlement, okay? All these analysis, so the archaeological or the cultural object needs proxies to be defined, and at the same time, it's a proxy of something much more general, which is always related to the nature or behavior of human societies, past or present human society. Okay, so how do we deal with this very problematic data? I mean, when you have very few examples, you use data augmentation techniques, synthetic data. When the data is very inconsistent, you can use approaches to create more consistent data, such as curriculum learning, reinforcement learning. When the data is very unstructured, you can use some machine learning approaches to create data that correspond to your own expectations. As you know, this is always dangerous, but if, for example, you have different types of survey, people walking through the landscape and collecting pieces of pottery, but in northern Italy, this survey was done with people separated 5 meters. In southern Italy, it was done with people separated 20 meters and walking around. But you have enough data of these surveys, all of them different. You can combine all this data to synthesize it in a kind of parameters that can be extrapolated to other cases and create a more consistent data set. Okay, this is something that is very interesting. This kind of the use of machine learning to create synthetic data that has not been used very much still in the discipline. So when another interesting thing is that the data is very concentrated or dispersed. Let's say I want to use a machine learning approach, a computer vision approach, segmentation approach to detect archaeological sites. For example, tombs. You are going to have lots of tombs, very concentrated, graveyard. And then there's not going to be any graveyard in 10 kilometers around. But then there's going to be another in which you have all the features very much concentrated again. So most of these computer vision systems will have serious problems in terms of not identifying objects when there's not much to do. They expect some consistency in data distribution. So you have to use approaches like negative training, background multiplication, doppelganger technique, in which you create areas artificially in which there's lots of background and not objects. Basically, there's lots of ways to deal with cultural data. And this is very important because as you probably have realized, most of these approaches require loads of computation. Okay, it's and not just lots of computation, but specific approaches, many of them based on machine learning. This is interesting because up until recently, we just couldn't use these approaches to create new data for massive analysis in the humanities. Now we can start doing this. So let's say we are now, I think, at the doors of a new way to incorporate the humanities in computational analysis. But I think the most important thing is how you design your question, what it is that you want to explore, what is the ultimate question you want to solve. This is what is going to determine which kind of proxies you use to define your cultural features, which kind of multiplication or data analysis approach you are going to use, and this is how you are going to be able to design your project. Okay. For example, with this kind of massive data sets, you are kind of reduced to a few types of data analysis, no? Detection, classification, clustering, prediction, okay? But taking into account the nature of the data, for example, the uniqueness of certain cultural objects, you can do analysis that focus on differences between them. For example, until what extreme a society was coherent in the design of tools. Is there much difference between them, or they are very, very similar? You can also make questions in terms of generalization to how similar is this society to this other. You need lots of data, but you need to group lots of small groups of data to answer this question in order to make a generalization. Okay, you can use this type of data to create definitions. For example, what is the nature of objects? If you have used different sources, like I was explaining, LiDAR or multispectral, you can use the indexes developed by this method to have stable general definitions of these objects, but then you can apply to other areas. Okay, in general, all these are very large scale, deep meaning questions. That is the nature of the data kind of force our research questions. We when you use large, massive approaches, you cannot go to very specific questions in a very specific time and moment, like, I want to know why this group of people settled in this area, okay? Which is a traditional archaeological question. You go there, you dig the site, you see the type of soil, you do an analysis on the area. These things you cannot answer with this kind of large scale approach. You have to go to questions like why the people were living in this type of environment, okay? They need to be much more general and deeper in a way. So going to start moving with case studies, so you can see some examples of all this I was talking about, okay? They are mostly archaeological, but I think many of them are extrapolable to other humanities. So up to now in archaeology and many other disciplines, movement, the analysis of movement was done with vectors. They were lines. What is the best way to move from this point to this point? And then you have a line describing this best movement, okay? I think this is a research that is very interesting because before the mid 19th century, communication required movement. You could not, you needed to talk to other person, you needed to move physically, okay? And this is not just important to develop coherent societies. It's also important to study how genes move, diseases, economy. I think it's very, very important. So I have been working with this project trying to create a multi-temporal movement analysis. That is, it's not the same moving in winter than in summer, using lots of different sources and using machine learning to integrate different cost factors. Okay, that is what is facilitating or making movement more difficult from a raster cell to the next. Okay, and using different factors I will show you and different origin and destination. Okay, so those are examples of factors. In this case, is the cost of the slope, how much it costs. This is an area of Iran between India and Mesopotamia. So it's a very large area, but just to show you an example. For example, in white here, very high costs because there's lots of slope. It's very difficult to walk upslope. This is a multi-temporal surface water. When there was water, at certain moment in time, okay? And this is where it was snow. I mean, when you start the algorithm, you have to say at which moment you want to develop the analysis, okay? Which period of the year and from which origin, destination, stuff. Okay, this is we have very few data of how much height affects movement, but it does, and you can use the few ethnographic examples we have to generate a cost maps in terms of height. This is wind chill, which is the temperature taking into account the average wind for every moment. This is the lack of water, which is defined as desertic areas without vegetation, power to heat. It's a formula developed out of ethnographic data, which aims to analyze how difficult it is to walk in areas where you are sweating and you don't have water close. Okay, this is very important for past movement. So yeah, there's lots of things, water attraction, like oasis, you know, types of soils developed with synthetic aperture radar and multispectral data over 30 years of analysis to create this. Well, and other things try to solve changes in the landscape done during the last 100 years. Okay, so this is an example of this type of analysis. It's not a line; it's a network of possibilities of movement for different periods between different areas. This is really interesting for specific practical applications. For example, this is the cost of movement between Istanbul and Xi'an, which it's the Silk Road. You know, many of you have heard about it. As you see, it goes through the Mongol steppes because this analysis was done for summer. So, I mean, it's very fresh in the grasslands and, very flat. But in winter, this is impossible. It's frozen. It would be. So it turns out this route is the best route to be practiced at any time of the year, both in summer and winter. And this is exactly the location of all the Silk Road related cities. This is very interesting because it turns out it has a very significant correlation also with the first cities. I'm talking about Uruk, Babylon, cities in India. You see what I was talking about, very large questions. What we are seeing here is probably that that movement was necessary for the emergence of urban civilization. I mean, cities only emerged during the last 8,000 years, but they all disappeared. But there was a moment that they all emerged at the same moment, and they maintained. They didn't disappear as before. And this is what this graph is showing us, is because they created a kind of network, and they were able to back each other. And this network, this communication, this self-dependence in the past was only possible to do through physical movement. Okay, so I just wanted to show you an example of how using these massive data sets can answer very large questions and at the same time very general. Okay. You see, there's the example of the early cities like Nippur, Tepeyaika, Mohenjo-daro. I mean, we are talking about a network that extends over large parts of Asia. This is quite interesting. Okay. Then, for example, once you have created this network, you can use more traditional approaches, for example, to study the permanence of cities. For example, the study of this type of analysis in the UK during the Roman period allow us to understand that those cities that have lasted through times were those that were better connected according to the Roman road system, which were the ones who developed the main network of roads in the UK. So I was saying very, very relevant questions to understand how we live today. Where do we live today? Okay. Also, from a more remote sensing perspective, I have no idea what's the timing for how long I've been talking. So
1:30.
1:30. Okay, well, I will go a little bit fast. In this case, I'll show you an analysis. There's this theory that the Indus civilization developed just like Egypt and Mesopotamia in areas where there were rivers that today have disappeared. We still have the Nile and the Tigris and Euphrates in Mesopotamia, but in northern India and Pakistan, many of these rivers have disappeared because we have lots of sedimentary deposits coming from the Himalayas. So one of my jobs was to reconstruct this network, and for this I use massive satellite data. Joining. I'll show you. This is an example here. Using vegetation composites for the last 30 years, and trying to see if there were any clues in healthy vegetation. Okay, you have some examples of the analysis. You can see some of these analyses show lots of paleo rivers, dark. Okay, you see they are darker, and in here, can you see? Yes, and in here you can see also very clearly the paleo rivers that have disappeared today. This is a desertic area, and still we can locate lots of channels that do not exist today. So yes, lots of examples. However, I realized there was some problems in terms of visibility. There were some rivers that were not appearing. And I thought perhaps this was what we were talking about, the question of how we define our objects of study. If we want to find rivers and I'm using multispectral data, I might be losing something. So what else defines a river? It's topography. It's lower than the surrounding area. No, it has to carry water. So it's kind of channel. So it has also a physical aspect and not just a physical chemical reflectance aspect. So we developed this kind of algorithms to analyze microtopographies. And compared to previous algorithms, it was designed for objects that change shape. That is, there were lots of topographical analysis methods directed to show things that had a stable size. Okay, but this method is variable. So if you apply the previous methods to different areas, you can see some objects, these objects that have the radius that allows detection. Okay, or some parts of rivers. But this one, the G here, allows you to detect things independently of how the width changes. Okay, that was very practical, and this is one of the first multispectral approaches I use, and this is the second, the topographic approaches. So you see, I'm using to define what a paleo river is. 5 different types of sources. Some of them are radar, some of them are multispectral bands, some of them are topographical bands, and all these sources have been treated to create a specific source that can define better what my object of study is. Okay, so I reach a definition that does not only detect my rivers, but is telling me something about. I mean, can you see the difference? We have these things. We have, can you see the rivers here? For example, this one in the middle, I cannot see the mouse. Here, this one here is very dark, okay? This approach is based on vegetation indexes. This paleo river, which today when I look in the aerial photograph does not exist, is dark. What does it mean? It's a vegetation index. Dark is low values, no? Generally, when you do a RGB or something like that, okay? That means that the vegetation is not very healthy there, okay? So it is possible. It was a river, it was buried. So what happens is that when you have this kind of sedimentary rivers with lots of flooding, okay, they flood and the thicker sediment does not move, it just goes down and accumulates close to the river. So the thinner sediment, the more clayey sediment floats and disperses, which is very fertile. Okay, this more coarse sediment that cannot float that far away from the riverbed stays close to the riverbed, and this is less adequate for cultivation. That's why we have darker things. So what it's telling us is that these rivers that appear very dark here are from a climatic period in which you have lots of flooding. However, you see, the ones that do not appear are the blue ones, deeper ones. You see, in here, the ones that correspond to the dark are topographically high because the thicker sediments accumulate and then create a talus, a kind of elevation, and the thinner sediments disperse. Okay, so those are these rivers corresponding to a period in which you have lots of flooding. However, these rivers that do not appear in the previous analysis are not depositional rivers. Those are erosive rivers. These rivers were not flooding, were just dragging sediment. That's why they are deeper in the ground. They are excavating the ground. So this definition, artificial definition we created of our object of study did not just allow us to define in a way what a paleo river is in terms of the sources employed, but also differentiate between rivers, which was one of the objectives here, to try to relate the disappearance of rivers with the disappearance of the Indus civilization. As we are seeing in this image, it's much more complex. Another thing we did with this project is try to detect archaeological sites in the area of the Thar Desert, okay? So yeah, for this we use also synthetic aperture radar and multispectral imaging. And yeah, you have the sources here, and what these kind of sources are telling us in terms of defining the object. The color, the vegetation on top of it, the chemical composition, the physical material. So you are getting more and more complex definitions the more data you you put. The problem is that this is a huge amount of data. So to do this, you need super HPC resources and very big data, and a method to analyze this, which is becoming increasingly more common, machine learning based approaches. Okay, so this is the result. This is a probability map, and as you can see, some of the sites are very clearly visible. Yes, these are some examples of the maps. Many of them, these ones that look, you see there's one here, another here, that look like the Rebel Alliance in Star Wars. You see, those are partly covered by dunes, or this one here. So you only see the edges of the sites. This is our definition of the feature in the different sources we employed. As you can see with LDA, this is quite a good definition because it's creating a very clear cluster here. So I'm not going to go into how relevant this is for archaeology. I'm going to say, because I directed this research, it's very, very relevant. Just believe me, they're super important. Okay. And we detected some new large towns that are very common in the industrialization. But, and you know, there's absolutely loads of new sites here, but if you realize they are in very specific areas. This area in white is the irrigated agricultural area, and this area in white is the desert with deep dunes. Okay, this is a very good detection rate, but it's very difficult to move this definition to another area. And this is one of the things we're trying to solve before. What I was telling you, this usually the definition of objects based on specific sources are very much constrained by the environment. The environment forms part of this definition. So one way to go is to increase the complexity of the definition of the object. You will never define the object using sources. They are always much more complex, but you can create your own specific sources to tackle the specific nature, or what you think is the specific nature of the object. Okay, so now we are talking about 20 different layers. This is a huge amount of data. So we tried this new algorithm with thermal data and some specifically created sources in the Fertile Crescent, when we have many of the first cities of humanity. And I don't know if you can see it already. My screen is visible, but perhaps not here. Can you see the dots? Let's make a zoom. You see, I mean, what this is telling us is, I mean, this is unsuspected. There's no site known here. Okay, what this is telling us is that we have been many, many more than we ever believed. You know, and through a very long period. It's probably, if you look at all these settlements and the area they are occupying, the density is much, much higher than the density today. This is because, of course, we are talking about 5,000 years of accumulated, but this is really unsuspected, and the range of knowledge of how to live in these difficult areas here, it's incredible. And it's very interesting because the algorithm has even learned to identify. You see, this is the white is the area the algorithm is identifying as high probability it's an archaeological site. But if you look at it, there are some ruins on top today. So the algorithm is realizing this is modern. So the old part is just below, you see, and probably around it. So the modern settlement put on top of the old. Okay. And it's able to identify things that are not visible in normal imagery. This is not visible. There's no way you can detect it if you don't go there on the site. Okay, this is with some specific analysis to see if these sites detected by the algorithm were actually something, because this is one of the problems. You get results. There's no way you can evaluate them. You know, they are telling you, okay, look, in this small area you have 300 sites. Like, okay, what do? Do I go visit them? What, in Mesopotamia now? Yeah, it's so this is a problem. So even though it's amazing the number of sites that there were in these areas in the past, you know, we have been everywhere, but again, we have to think our definitions are not covering the full spectrum of what an archaeological site, an ancient settlement was. So what do we do when archaeologists the traditional thing, you go to the field, you walk the area, and you look for pieces of pottery, metal, that are telling you that at some point in there was somebody living or doing something. Okay, so we did something similar. We created a system with a drone that is able to scan a big area and detect pottery automatically with a segmentation approaches. That was our first approach. That's our second. The algorithms are below, and now we have been able to put this in a video. It's in the left. Can you hear the sound? No. Okay, because the video has some sound, and now and Ivan we're talking. Can you see how the area in black and white is illuminated every time a pottery piece is being detected? So yes, this is really cool because it offers us to extract the georeference shape of each individual fragment in real time without the need of photogrammetry or SLAM, no data consumption, very little processing, and we have the results available immediately. The platform here was just a mobile, but this means we can put a camera in a rover, in a small robot, and just walking non-stop and charging when the battery goes low. So you come back to base, recharge, continue, and you can do a swarm with it. So what this allows us is to actually survey very large areas very efficiently in very low time. And it's not just that, it allows us to extract the shape. So these are comparison of this analysis, this type of detection with traditional methods. In this case, you can even analyze the cluster. And I'll tell you, you can even correct the presence of vegetation with these approaches. And if you have the shape of every pod set, you can also extract their orientation, how eroded they are, their size, and you can do analysis that allow you to tell you if a site is in danger or what is the actual center of site, how it's being affected. You can do lots of stuff with this. This is an example of visualization with this. But another interesting aspect, moving beyond sites, and you must be a bit bored, it's a three-dimensional data. Many of our cultural objects are three-dimensional. And frankly, in humanities, what we have done with three-dimensional data has been basically recording and visualization. Everybody loves to take a 3D object and turn it around for hours. Zoom in, zoom out. It's very cool. But there's very little research put into 3D objects. Okay, this is a very basic example of LiDAR data used to reconstruct a landscape and then simulate a flooding event and see how archaeological sites are very, very aware of flooding events. So they are all located in the areas where they cannot be affected by flooding events. That's what's the other explanation? That the ones that were in flooding areas, they did just disappear. So archaeological data can be very, very useful for these kind of things. It will tell you lots of information of what is the best place to put a settlement. In this case, we use this LiDAR data to detect almost 10,000 mounts. In this case, we employ an hybrid approach. Usually, you only have one approach to detect tumuli, burial mounts. But in this case, we combine multispectral with topography, and we got very few false positives. You can use it to reconstruct the excavations and analyze them, and you can use it to reconstruct the cultural heritage, like in this case, Greek temples. That's a survey we did a couple of years ago. And the interesting thing about this is not just the reconstruction, is that you can, I don't know if you can see it, but there's the horizon here, okay? There's the horizon line. The horizon you can see from this exact position. And those are the stars you can see from this exact position. This is a project in which we wanted to analyze the meaning of religious rituals. Okay, and for this we were using reconstructing these temples and getting them. This you will have to forgive me because this is something we did when we had still not rendered the temple. It was very heavy, but this kind of approaches, these phenomenological approaches, allow us to test theories on why the temples were where they were. Which star appears during the ritual of this goddess, if this is related to the location of the temple, to the situation. And the last results on this, I'm not going to say much because Rossini, which was directing this project, it has found lots of stuff in terms of the location of the stars and the temple and how they align in a certain moment where the ritual of the main deity of the temple was performed. So I'm not an expert on this, but yeah, it's kind of see if I can stop it. Okay, for other things, for example, with seeds, that's when we excavate an archaeological site, we find lots of bones and seeds and material. And you usually can say what they were eating, but in theory, we could say much more than this. These seeds, for example, were scanned and treated to align them and to make them coincident, and then we defined them. We took this 3D shape and defined them using the spherical harmonics coefficient. That is how well, I'm going to say it very basically, how well a shape adapts to a sphere. Okay, so this is a way you get like hundreds of coefficients to define these shapes. And one of the interesting things we found is that the scanner is very good. We use a very good scanner, so there's very little differences when you scan the same sheet several times. Okay, when you compare between sheets that are not the same sheet, they are different sheets, but they were grown under the same conditions, there are more differences. And when you compare seeds that were grown in different conditions, with more rain, with the differences in shape are very high. This told us that perhaps we could use the shape of the seeds to analyze how these seeds were cultivated, how they were grown. Okay, and with a combination of spherical harmonics and a multi-layer perceptron, we got a 97% of it's a very high. It's extremely high. I mean, take into account these things cannot be said by any archaeobotanist. The differences, I mean, a seed is less than 1 centimeter. They look all the same. I mean, I cannot differentiate between seeds anyway. I cannot even differentiate between fruits. So it's really one of these things in which this analysis, which is very mathematical, allows you to see things that are invisible. Okay, and you see, this is one of the points I wanted to make with the whole presentation. Is not that the humanities are benefiting from these methods. I think the humanities have a huge potential to impact other fields. I mean, you saw the images before, where you have archaeological sites everywhere. I mean, climate proxies today, you have to go to very specific areas, or wetlands for pollen, or specific calcareous caves for stalagmites, or you have to go to the poles to get isotopes, oxygen isotopes. Archaeological sites are everywhere, and this indication, this kind of analysis, I mean, I was interested in how they were grown, how ancient societies were cultivating, but it's giving you information on how you survive specific climate, which seeds you select for specific situations. If you do the same with seeds that are natural, in sites you have seeds that have been cultivated, but you also have seeds from natural plants that fall. Or when you collect the grain, you collect other seeds. Okay, if you have a good database of seeds that are natural, you have natural environmental conditions. And at the same time, you can use as a climate proxy, this kind of natural seeds. If you have the cultivated ones, you can see which kind of agricultural regime were doing people in the past to adapt to a specific climate conditions. Okay, this is You can do this with phytoliths, for example. In this case, this is another case study. I'm sorry, I have not worked that much with text, Mariana, but with maps, with Ivan, we developed this project in which, well, now today we have finished with the whole area. We have many thousands of maps. So basically, you use these maps to extract cultural information. It's going a bit slow, but you see, these maps show this kind of features here and here that are archaeological sites that have disappeared today. So it's going very slow. I don't know why. Somebody has disconnected my internet access. Okay. Okay, so I'm going to try to finish. So basically, these maps show a landscape that have disappeared. I mean, these maps are from the beginnings of the 20th century, and many of these maps have disappeared. So we can use these maps to extract the information of how was the archaeological landscape in the past. So I'm going to go directly to the conclusions. Of course, you can use satellite data to see how many of these sites have disappeared today. And this tells you that perhaps in 30 years, we will have very few sites remaining if the urban agricultural expansion continues as it is today. Just to conclude, because I'm told I should leave some time for questions. I just wanted to say that these techniques has huge potential to automate tasks, but also analyze phenomena or data or features that are not visible or apparent. They can improve a lot the analytical capabilities of humanities disciplines. But I think the really important point here is that the humanities research has the potential to explore human nature, behavior, and its consequences thanks to these specific approaches, the elements we use to study human societies, but also because of its diachronic scope. We are studying 99.9 of human existence, okay? More complex data, but I mean, this data is very complex. But today, thanks to HPC, machine learning, and other approaches, for the first time, we can study this data. This is very important because we have to stop thinking of disciplines as isolated things. I mean, as you see here, all these analyses where the only thing that was archaeological was the question. I mean, using geographical, computational, LiDAR data, satellite data, you know, and if I apply for a grant in geography, I will probably not get it in this country, ever. They would tell me, no, you are an archaeologist. I mean, this is a huge problem. We'll have to start thinking of questions and stop thinking of disciplines. And I think this presentation aimed, in a way, if you look at it this way, you realize the huge potential of doing so. Because at the end, the questions, when I try to solve a question about agricultural regimes in the past, I go direct to analysis of climate change. You know, I mean, I think is very important. And it's very important because most urgent crises today are social and human. So the questions are social. Even if you are using very computational based methods, you know, you are addressing questions and are going to be used and are going to be applied to social and human basic needs. So let's try to, I mean, that's one of the things of our department, no? Try to break these disciplinary barriers, try to work together on specific questions, not on specific techniques. So thank you very much. That was the end of it.
Thank you.
Hope you like it.
I want to say first, just briefly, that thanks for the excellent talk, and all the great points you make at the end too. Well, at the end and the beginning. Also, I knew already how your projects, how impressive they were, how great your research is. But I was fascinated to see also the similarities with astrophysics, astronomy, and cosmology, because I mean, sometimes we think of cosmology as the archaeology of the universe, right? And there are a lot of similarities about the methods that you, the techniques, and the approach that you take in this computational archaeology and computational humanities. So this is great for me too, in terms of even more inspirational what you're doing. But I have two quick questions and give people time to ask a few questions. We have time for a few questions. One quick, I'll see if I'll remember because we're in different places in the talk. In one time with the paleo rivers, how do you validate the results? I was curious. And the other question was that in the when you say that for the detection of the with ML of the mounts, right, the sites, right, that they had a high probability when you show the shapes that looked actually like a bunch of galaxies.
Yes,
but just by
actually.
coincidence. When you show that and you said high probability, so the white, how probable it is? What are the numbers quantitatively? What is the probability that was going to be decided? Because you probably you showed it all as black and white, but at the same time there might be some places where it's more probable that you might want to go and check to validate that, that there is something there.
Yes.
So those two are questions, and I'll open for 4 to 5 questions if there are some from the online or some from here.
Yeah, the validation is usually very standard for the ones in the edge of the desert that were in color, let's say. We just retain a percentage for training data and see how well it detects. And then we also had a series the maps. From the maps, we extracted mounts that have disappeared and today are not visible. So we could check, and also from archaeological surveys in the past. Those are perhaps archaeological surveys had only 10 sites. The maps show the 10 more. So we have a way to create an estimation of the probability, how accurate it is. It was very accurate in this case. In terms when we applied it to the Fertile Crescent, it's an area that has been the focus of many archaeological investigations. So we had some data sets to compare with, and found all of the sites and many more. The problem are the many more, of course. we cannot we cannot send anybody there, but yes, in many cases, when we have very serious doubts for some areas, we use multispectral analysis and try to use topographical analysis and see if there were some indications that it was coincident. So we validated this. With the rivers, we couldn't because many people have tried to do a correlation between the distribution of sites and rivers, so, with a Kolmogorov Smirnov test to see if they align well. But I believe that with these erosive rivers, imagine once you look at Mesopotamia, it is like full of sites. Imagine what will happen if you put an erosive river through there. It's going to do like that. It will follow the slope, but 1, 2, 3, 4. So at the end, it will erode, destroy all the sites in its path. So at the end, you will have all the sites aligned to them because they have destroyed the ones that were there. So I think it's very difficult. The team at Cambridge went to the field and they actually made holes and tried to date them. But with erosive rivers, it's very difficult because this is alluvial plain. So, all the deposits come from rivers. So there's river deposit of a river deposit. So you never know when you are dating this river or previous one. It's very complex. In this case, I think it was more a geomorphological approach. We know what is the physics and the behavior of these rivers, and all of them made pretty good sense from a geomorphological point of view.
Okay, great. Thank you. Questions, Alejandro?
Yeah. First of all, it was a fascinating talk. It was very impressive, and I think it has like a huge potential. And I only have one question. and it was of the algorithm you use to forecast settlements and so on. Are they like very context dependent, or you can use them in other areas, other countries and so on?
They are very context dependent. Yes, that's extremely complicated. What I was developing, the last thing you saw actually is a series of nested algorithms that have that train. There's lots of information for this area. So what it does is kind of goes to a specific area, uses the information for training and the specific environmental background, then analyzes what sources adapt better and does the analysis, then moves to the next. Well, first it just segments the area and applies the algorithm selecting specific sources in different areas. And what you saw, it's a kind of union of these multiple algorithms based on different areas. That's why it's such a wide area. It's covering different, and in some areas it works better than others. But yes, it's quite efficient because basically you are using like 20 different parameters to define what the site is. However, I'm pretty sure there are lots of sites that do not adapt to this definition, or they are not mounts. Perhaps they are sites in which they went specifically to collect a specific type of resource. So at the bottom, yes, you can do a good job, but you are losing the most interesting type of site. Is the one you don't know. So I mean, you have to be careful because at the end you always end up confirming your own definitions.
Okay.
Another kind of question. Maybe. I'm interested on the use of synthetic data on your research. You mentioned twice in your presentation. The first question is which experience you have, if you can tell us about using synthetic data in data augmentation or creating new data from real one. And the follow-up question is about these new techniques of synthetic generators that can generate data based on certain conditions. For instance, Responsible AI, they use this synthetic data generator to create more gender balanced data. Oh, you have a condition, a pre-known condition, and then you can perturb this data generation process to generate a more fair.
Yeah,
that's great, but this kind of conditions doesn't need to be tied to responsible AI things. Maybe there's some knowledge that you have that you know about the field, but are not present in data that you can embed in the data. And my question is, if you see that this approach is interesting for your research, and for instance, there are new approaches who try to embed causal models inside this synthetic data generator.
Yeah.
And what do you think about this?
Yeah, I'll answer this first because I forgot the first question. So yes, I think they are essential, and they are going to be more essential as time passes. I mean, I think the computation side is more or less well advanced. The algorithmic side, we see I mean, they are still improvement, but the improvement in the systems is not that huge anymore. So I think the big area of advance is the data itself, data creation and synthetic data in particular, because as I was saying, it's a question of definition and the expertise. In this case of archaeologists, in my case of archaeologists, always makes a big difference. I mean, you see the worst results in teams that they have engineers and archaeologists, and the communication is not good, because they don't reach good definition. So in my case, the use of synthetic data, and it's mostly based in my knowledge of what it is that I'm looking for. Okay, Ivan, which has developed several data multiplication systems. Actually, I think he wanted to add them in our repository. So yes, like argumentation, but more directly to archaeological case studies, will tell you that it's impossible to work in archaeology without this approach. I mean, because you never have the data, and much of the data is restricted by the poor definitions. If you only use shape, you are going to find 2,000. So most of the approaches that do not use data augmentation, synthetic data, and negative data are completely useless.
What do you mean by negative?
Negative data is data that define things that is not what you are looking for. For example, it depends on the algorithm you are using. It is called background, or yeah, but in some other cases you might want to create a multi-class algorithm, and several of the classes being things that you don't want to detect.
Like the signal versus the noise. The noise is the
Yes, I don't. What was the first question? I forgot.
No, your experience using the data method.
Yes, that was yes. It's. I think it's yes, absolutely necessary, and in some cases, very curious when like curriculum learning for the maps, Ivan actually draw the mounts as they should be drawn using this 19th century system, hatchers. I mean, none of them was drawn like that. I mean, you look at the maps and they are all very different, but I mean, it's curious because the idea of the surveyor that was drawing the map was this exact thing. I mean, then with the time and the house and how he did it, none of them are actually like this. But the average shape, the average idea of this shape was this, and there was no single representation of this. So the use of a curriculum learning in which you first train the algorithm with this ideal data is very Platonic in a way. This idea of the ideal world in which the objects are what they should be and all the rest are just poor imitations, and then you create this curriculum synthetic data, and amazingly, even though none of the actual features in the map look like that, then the second training, you use the real data, it works much better than just using the real data. So it's very surprising. I mean, it's very surprising, and it's quite poetic to think of what you are to detect as an ideal thing, that the actual real implementation is very different, but it always goes around this idea. That's what models are. Yes, yes.
Question here in the chat, or Hector, or if not,
There's
if
something
it
in
is,
the chat.
no more questions, we're gonna thank Hector again.
Okay. I think that's okay.
And have conversations with him in any other time.
Thank you. Thank you.